In this problem, we've got a current that flows down some wire towards some point P, then stops, forms a circular arc, and then flows outward away from P. And we want to know what is the magnetic field at this point P. Well, first of all, this is kind of a convoluted setup. You know, why do we care about this? This is actually a very important problem, a generalizing problem, because as we'll see at the end, we'll use this setup to extend to a full circular loop, which is something that comes up all the time, and we'll be able to calculate what the magnetic field inside that circular loop is. Okay, so first we start where we always do, with Biot-Savart's law, mu naught over 4 pi times I ds cross r hat over r squared. And we also note that we have really 3 distinct sections here. We have section 1, section 2, and section 3. Because different things are going on in the different sections. So let's just look at them individually and add them up. And note that, let's look at section 1 first. So, dB is going to have some magnitude and direction. So let's look at the direction first. We've got current flowing down this way, and r hat, which is in the same direction, r hat points towards point P, which is in the same direction as the current. So since those two things are pointing in the same direction, the area of that parallelogram that mapped out by, the 2 vectors, which would be my 2 fingers here, that area is 0 because they're in the same direction. So this whole thing is 0. Let's look at it another way. ds cross r equals the magnitude of ds times the magnitude magnitude of r hat, which we know is just 1, times sine of the angle phi dsr. Well, this angle is 0 because I hat points in this direction and I points in this direction. ds here points in that direction. That's the wire that we're integrating along. And r hat points in this direction because the vector r connects ds to the observation point, and r hat is the direction of that. They're both in the same direction. Sine of 0 degrees is 0. So dB1, I'll call it, equals 0. Well, what happens here? Section 3. Well, this is this has some magnitude and direction like before. And let's look at the direction by looking at this cross product, that part of Biot-Savart's law. So ds cross r hat equals magnitude of ds times the magnitude of r hat times sine of the angle between ds and r hat. Let's call that dsr. Well, point your index finger in the direction of the first vector, your second finger in the direction of the second vector. Well, now we've got a 180-degree difference between these two. The area of that parallelogram, again, is equal to 0. Sine of 180 degrees also equals 0. So this cross product equals 0. So the magnetic field all along section 3 equals 0. So the magnetic field at point P from this section and that section is 0. Now, that doesn't mean that there's no magnetic field from these sections. There's going to be a magnetic field here, for example. In fact, that's going to be out of the page, and here the magnetic field is going to be into the page from this section of wire. But the magnetic field contribution at point P from section 1 and section 3 is 0. So therefore, we only have to worry about this circular curved piece of wire. I'll zoom out just a little bit and get more of the page in. Okay, so section 2. So dB equals mu naught over 4 pi I ds cross r hat over r squared. Well, we know r squared is just going to be a because that radius is constant the whole way around. Let's deal with this cross product real quick. So ds, we could call it ds2 if you want, but you just know that the s is different for each one of these, as is the r. So ds cross r hat is equal to the magnitude of ds times the magnitude of r hat times sine of the angle between ds and r hat. I won't put the symbol in there. Well, what's the direction of ds? Well, that is tangential to the curve at all points. ds changes. It is in this direction at the very beginning, and as you move along the curve, the direction with which you're moving changes. So ds's direction changes. It's always tangential to the radius that points towards the center. It's tangential to the curve, a right angle to that radius vector. So phi dsr equals 90 degrees everywhere you go along this circular loop. So sine of 90 degrees is equal to 1. So ds, since this is a vector, I also need to add the direction here. So this is kind of hard to do where I'm sitting, but my index finger points in the direction of ds. Let's say this spot right here. My second finger curls in the direction of the r hat vector, and my thumb points in the direction of the cross product. My thumb is pointing into the page if you couldn't see that. So that is in the negative k hat direction. So ds cross r hat equals the magnitude ds times the magnitude of r hat, which, remember, the magnitude of r hat is equal to 1. The r vector has some magnitude equal to a, where r vector equals the magnitude r times r hat to give the direction, and in this case is a times r hat. But here we're just worried about the magnitude of r hat, so let's just multiply by 1 times 1 again. Well, what is ds? Because we're going to have to integrate this along something, right? Everything is constant except the angle theta that is changing. So if we say this is 0, then down here we traverse some angle theta. So this is going to be at some angle d theta. Well, if you remember from circular motion, s equals r theta. Some arc length s is equal to the radius times the angle subtended by that arc length. So ds is just equal to r d theta, assuming r stays constant. Here, because r is equal to a, say ds equals a d theta. So this vector ds cross r hat is equal to a d theta times 1 times 1. So we'll take this, and times negative k hat. Forgot that again. So we'll take this whole vector and dump it into Biot-Savart's law. Right here. And we also have to say that r squared is equal to a squared, and put that in as well. So dB is equal to mu naught I over 4 pi, pull out all the constants, times negative a d theta k hat over a squared. I'm going to move things around a little bit, simplify it some. So that's negative, this cancels that, mu naught I over 4 pi a d theta Actually, let me put the k-hat like we did on another problem. I'll put the k-hat in here, so then I just have all the stuff I'm integrating on the outside. How do I get the total field? Well, I have to integrate this. Integrate that. So the total field at point P is equal to negative mu naught I over 4 pi a times the integral of this. And if I evaluate it from 0 to theta, this becomes theta k hat. And that is a vector. Should have a vector bar on it. So for a complete loop, too many O's. For a complete loop, you want to integrate from 0 to 2 pi. So theta final equals 2 pi. Put that in the expression I've just found. B equals negative mu naught I over 4 pi a times 2 pi k hat. Well, the pi's cancel, the 2 cancels, that becomes 2. So B equals negative mu naught I over 2 a k hat. Now the direction depends on which way you choose to be the positive and negative and so on. So most of the time you'll see this just written as the magnitude of the magnetic field at the center of a loop is mu naught I over 2a, where a equals the radius of the loop.